I'm James Byrne, Research Software Engineer for BAS, British Antarctic Survey. I'm also a 2022 Software Sustainability Institute Fellow, which is, the principles of the SSI have very much driven the sort of mechanisms of development behind this, as hopefully you will see. I've got with me Tom Anderson and James Robinson. If you guys would like to give a very brief intro to yourselves.
Yeah, I can go first. So, as Alden said, I'm a data scientist at British Antarctic Survey in the AI lab, the same team as James Byrne here. And I led the kind of initial development of the deep learning sea ice forecasting system that James will be talking about today. That involved kind of creating the initial code base that was very much a research code base. And I suspect some people in the audience will know about research code often not being having a lot of errors and not lending itself very well to operationalization and things. So once I finished developing the deep learning system, the Jameses came along and worked their magic to make the code base much more functional and operational and tidy. The initial code base, you couldn't say run the AI system in real time very easily. So lots of interesting benefits will be presented in this talk. And by the way, I actually have COVID right now for some people who were listening in at the beginning. So it's very good that this is remote and virtual, so I'm not infecting everyone. Not that I would have actually attended if this was in person, just to clarify. But yeah, really exciting project that will be presented today. So I'll pass the mic back.
That's great. And James Robinson, if you'd like to just give a quick intro.
Yeah, hi. I'm James Robinson. As Alden said, I'm a senior research software engineer at the Alan Turing Institute. And I've worked with James Byrne on, as Tom just said, sort of productionizing this IceNet code and getting it to produce like daily predictions, which James will talk more about.
Lovely, thank you very much, chaps. We'll start off with the abstract. Hopefully you've been having a little bit of a skim read of that. It was in Tom's lightning talk video as well. Basically, as Tom has rightly pointed out, he undertook a load of research in order to exemplify that deep learning can be used for seasonal sea ice forecasting. It was very innovative, and we basically then built a project as RSEs around that in order to develop the code base and also to move towards a real-time forecasting system for both poles, where the original research was in the Northern Hemisphere, and also to move towards a daily timescale. So I'm going to give you a whistle-stop tour. We'll start technical and we'll abstract out to the less technical, more holistic picture of IceNet. But please don't be put off by the intense technical start, because especially if you're non-technical, we'll start with a look under the hood, but then we're going to move on to the use cases and the big shiny integrations, which will be a lot nicer to understand. So there's a little bit for everyone in here. And then we're going to try and leave a load of time for a Q&A at the end. So I think one of the reasons that I'm doing this is because I can talk insanely fast if I want to, but I'll try not to overdo it. So we'll scroll down a little bit. This is all the jokes and notebooks to go through. As we've said, IceNet is a tale of two halves, this being the second, the first being Tom's very important research into demonstrating that deep learning can be used for seasonal sea ice forecasting. The second is basically making it so that we can move towards a larger ecosystem around the research. So what we'll cover, the bubbles denote the increasing capabilities associated with the deep learning research built around the original model, which became the core driving force that continuously expands the capabilities and functionality of the bubbles around it. So that will become clearer as we abstract out. In the agenda, we're going to cover the pipeline and model operations that facilitate adoption of the model and thus research and forecasting operations into the future. We're going to move on to the environments and extensions that allow these pipelines to be reproduced and accessed easily, promoting FAIR, that's definable, accessible, interoperable, and reusable principles for data access. And then we're going to move on to the integrations and applications, which is the surrounding framework and ecosystem that expands the adoption of IceNet through integrations and applications. So this is really pivotal when considering the data products of the pipeline and how they fit into a data-centric ecosystem. And it also underpins the decoupled interactions required for our larger digital twin initiatives that are taking place both within BAS and the Turing. And then at the end, we'll have a bit of a look into the future, some quick conclusions, and then hopefully a lot of time for some Q&A. So I'll dive straight in. So if you remember, the first and the most important bubble at the center was the model. Now this is a unit architecture, very, very deeply layered. Excuse me, I'm just scrolling my notes. And the paper explained that the proving of this model for the paper explains this model for CI forecasting better than I could. It's linked in the document that has been is associated to this talk, and it was published in Nature, and it was Tom's hard work which did that. There are a few pros and cons that we can consider, as Tom pointed to, about a pure research code base, though. So the pros first. The original research was focused on science goals, and it proved the capability of what we were trying, or what Tom was trying to achieve. Another pro is that the researcher in that case focused their efforts on the research, unencumbered by oversight of non-tangible future developments. Another pro is in the publishing of the excellent research driving project like ours to consider the operational picture. But there's a few cons to inheriting this research code base. The first is that you often don't inherit a development code base appropriate for sustainable operational use. Another con is that the bar to future adoption is implicitly raised, be it for scientific or operational purposes. This is largely down to the complexity and the sort of specific authorship of the code base. And the third con is that you are in danger with these types of research code bases of it being left on the shelf, with research not really understanding why, because perhaps they weren't necessarily schooled in the first place in the art of sustainable software development. Thankfully, 1 researchers and 2 RSEs followed the project up through the Turing BAS collaboration with a view to addressing these pros and cons. So we then move into the next bubble, if you remember the funny little diagram at the start, and this is the pipeline bubble. So the reproducible research is all good, but adaptable research is better. And this is what we did with Tom's code base. We turned it into a Python package. And we looked, my background's in DevOps primarily, so we looked at how we can actually create ephemeral environments for a variety of researchers and operational uses of the code base. This also was the point at which we decided to look at how to move towards a daily forecasting operation model rather than the single the monthly forecasting, and also look at both hemispheres. So this looks like quite a complicated diagram, but we'll go through it in a few more bits, in a bit more detail as we go through. We're just explaining the bubbles at this point, but I'm scrolling the wrong window now. Next is the framework bubble. So this was James and I designed the project around Tom's original research. So down here in the bottom left, you have your model operation. So that's using the pipeline code base that we've just talked about. But then we have a layered architecture around it. So this generates some forecast output, which is then ingested and made available to researchers as NetCDF based data. And that also has an extract, transform, and load pipeline, which populates a database suitable for use with an API platform. That API platform then allows us to look at external partners in order to, for collaboration's sake, and also to drive things like web layers and other applications that might be suitable for use for more general dissemination of the forecasts. And then moving on, we go to a larger ecosystem. So this is the example we're going to use throughout this talk, is the Sir David Attenborough digital twin, the traditional the ghost ship iconography symbolizing that. And you see that IceNet actually sits within a much larger ecosystem of items or data producing items within that digital twin, in order, in this case, to actually do route planning. So these highlighted items are the basis for a route planning system that we have. So that's a quick overview of the bubbles. We're now going to go into the part of the agenda which is around the pipeline operations and model operations. You see that I've got some cheeky setup. Ignore that. That's just to get a load of packages which take a bit of time. And I'm running this on our little HPC. There's a limit to, unfortunately, how much we can do in terms of obviously downloading and processing data, but this hopefully gives you a bit of an idea. Now, we have many repositories associated with the ecosystem, but the important one is the IceNet pipeline, which gives you a demonstration of executing the Python package in this wider pipeline schematic. So we install an IceNet 2 installation, which is the Python package, and that gives us a load of commands that we can then use in order to process the various elements of this pipeline. So in the first instance, what we have is a source data store, which contains all of the data that we download from external sources in order to train and predict and the like. This can actually be common because the source data obviously isn't going to change over time, but it might change in the context of an individual researcher's environment or operational environment. So we have a few steps here. I'm scrolling along the window again. We have a few steps here. We generate the mass data, which is commonly used data, so that we know where land and polar observation gaps and the like are in both hemispheres. In this case, we're going to do the south. So you'll see that I have I've processed that before. We're also going to download some ECMWF Era 5 reanalysis data. This is climatic reanalysis data generated against forecast models for historical periods, and also we're going to download some ocean sea ice satellite application facility sea ice concentration data, which is otherwise called OCSAF data, but I'm trying to avoid the acronyms. And this is sea ice concentration data taken from microwave observations which go back to 1979. So we're just downloading a small portion of this data, and this is effectively our ground truth for training the model. So at time of writing in the IceNet package, we currently have the ability to download Era 5, CMIP, which is the larger, the very famous climatic data set. We have HRES, which is real-time forecast data that's available from the ECMWF for research purposes. And we have as I said, the sea ice concentration data. Now, the reason we have commands like this is to lower this barrier to entry for adopting the model. So these three commands, the masks, Era 5 and sea ice concentration commands, are equivalent to writing all of this code here, basically, which is not a lot of code, but actually when you're a researcher coming into this, it really lowers that barrier and allows people to get on board. Now we have our source data store, we can now consider actually processing that ready for training. Again, we have a few commands, and they're associated with the original. They're associated with the original data that was downloaded. Now, the purpose of these commands is for normalization and data conversion that takes account of training assignment of data and is prepared specifically for each data set. So it's specific to this environment and the training run that you're doing, whether it be operational for research purposes or with some modified code and the like. So very easy, and I won't run these here because they take quite a long time to do all of the normalization, even on relatively small data sets. But we leverage things like X-ray and distributed computing via DAS to actually do that normalization. And again, these are shorthand commands that allow us to do that are taking the place of this code here, which looks a bit more onerous, and as you can imagine, might be a bit more of a barrier to entry for people to understand. hopefully you're getting the impression though that actually like having both method is a really good way of allowing people to extend it, because of course if they do deep dive into the code, then they can just start creating their own data downloaders and processors. So next, there's a little piece on visualizing data stores. So visualization of CI's concentration from the normalized data files that's going to be used in dataset generation for our toy example. So this is coming from the OCSAF. If you remember, that's the CI's concentration ground truth data that we have. And we can visualize this because we've architected a common approach to all data loaders and data processors. We can quite happily just swap out for the Era 5. I think that's temperature at sea level, or temperature in the air actually, variables, and we can start to look at all sorts of different variables. I mean, I won't do too many here, but this is the same for the data folder, the original data store folder as well. We can start to look at various different bits of data without actually worrying about without having to go off and find files and all of this sort of stuff. And that's because we've got a well-structured file system underneath it. There's actually also commands specifically for that, one called IceNet video, which allows you to do it even more easily, but I won't go into that here. So in creating the training data set, which is taking your normalized data, we produce cache data then for training via TensorFlow datasets, which is the model platform that we're using, or the ML platform we're using. This is far faster for training with flash SSD storage. So GPU training nodes then sucking lots of normalized data off the network, or even building it on the fly, because for training IceNet, there are, the data sets do run to multiple terabytes. So what we do is we create these TensorFlow data stores, and then when we're predicting, we just build on the fly. So you've got both options. And actually, for the toy example, which we're having a look at here, if you drop this C switch, if you drop the C switch, then you get a load of cache data, and then if you put it in, then you get on the fly configuration that you can use for predicting. So in training predicting, I've just this was a previously run example, but again we've got a simple command, called IceNet train that wraps up everything into a nice little CLI wrapper. The output of that, I mean, as I say, this was a test run, but the output of that was, finishes with some weights and biases integrated results. So weights and biases is an online platform you can use for easy visualization of your model runs. And we end up with some model weights that we can then pick up and run again as down here. So actually I can just take those model weights and I can feed it into that wrapper. And I can, once again, I get a whole load more. In fact, I shouldn't have opened that, but you get the whole TensorFlow training run, once again finishing with your metrics at the end. So next we would move on to, so we now have our network weights and our train model. We now move on to load generating some predictions. So for every data load that we prepare, there tends to be some test dates that are associated with it. We can pull those test dates out, which gives us some dates in 2017 used for this example. And we can say IceNet predict, which is another command, once again picking up the weights and feeding some data from that loader. And it opens up a horrific TensorFlow window, which at the end spits out a load of NumPy files that are the results. We can then use IceNet output to actually pick that up and process those training dates in order to produce ourselves the net CDF output. And if you remember back to what I was saying earlier, that is the that left-hand blob of the IceNet framework. That bottom left-hand blob spits out net CDF data ready for researchers or the ETL platform to use. That's the extract, transform, load platform. Now, this is only half the story, because I've just run you through the commands that are involved with training involved with training a single model. The IceNet pipeline repository that we provide actually uses a tool called Model Ensemble in order to run training and prediction ensemble. So we run n number of models all at the same time, and they're managed on our HPC using that tool. And the same for the prediction. So actually, when you then run IceNet output at the end, which is run as part of the ensemble, when you run it at the end, it's actually picking up from 5 or 10 models, and then it's producing the aggregated results of those model outputs. And then we can use our IceNet upload commands, and those forecasts are then poked into in this case, Azure, which is where James Robinson was very good to develop the ETL and the API systems that underpin the ingestion of that NetCDF. Anyway, and then you can do a bit of forecast analysis. So for the sake of this example, I am using a daily forecast that we run internally just for testing, and I will run that. Like, why not? Why not? So this is actually the daily forecast, which was produced. I don't know when the 22nd was, but that was yesterday, unsurprisingly. And the forecast, we forecast 93 days into the future. Now, this is still an active area of research, but it gives you an idea of what I was saying about the ensembles, because we run through 5 models and we produce the mean standard deviation associated with each one, and it's all CF compliant data as well. So this is for the Southern Hemisphere, and as I say, this is still an under active development, but it just gives you some indication of what's going on. So the model's still under active development. It's not these aren't accurate forecasts, but you can see that it's outputting something which is vaguely realistic, which is great. And then if you compare the forecast, you get an image like this, basically. Again, so this is compared against the ground truth data in order to give some idea of where the errors are. And as you can see, there's quite a few errors. So and after that, you can then start to visualize the output. So this is visualizing the output. If you remember, I said it was a 93-day forecast. So this is actually taking one forecast seeded yesterday, which would be forecasting the ice for today up to 92 days ahead. And yeah, it's just a little video, so you can see it doesn't actually really track very well, but that's because this is a very trivial model. So taking a little breath, and then we are now moving on to the environments and extensions. So that was a really technical, potentially horrific deep dive into the inner workings of IceNet and the pipeline, but hopefully quite illuminating. And this is where we actually start to say, well, this is how you might begin to use things. Use the IceNet products. So environments and extensions. The first thing we'll do is talk about abstracting away from a single pipeline run. Hopefully there's some appreciation that we can base many pipelines around the same data store. So this little data store here is actually a common data store used across many environments. And for the sake of demonstrating that, when I look at the pipeline directory, which sits in my IceNet folder, that actually links to a blue environment. The blue environment is just one of 2 environments that I run operationally internally for testing. But they all use one common source data store, if you remember. So the way that we do this is using something called symbolic links. So every environment actually points to the data store one up from the pipeline that's running it. And this gives you an idea of how simple it is actually just to implement these ephemeral environments that can all point at one data store. So this is this is the simplest way of going about it, of course. And then to run, as I say, we provide some convenience wrappers in the form of in the IceNet pipeline repository, and one of those is called Run Daily, which allows you very trivially, once you've trained your models, to actually just put in a scheduled job. So this is a cron scheduled job to run at 9 o'clock every morning, activate the IceNet environment, and then look at whichever pipeline we're pointing at. So in this case, the blue, you'll see that I had AIUK, which was our very trivial model that you saw earlier. And it will then run the predictions for that day for both hemispheres. And as part of that, we do a local upload for some of our integrations that you'll see in a minute. So moving on so I've just kind of explained what Run Daily does, but what it does, it downloads using the IceNet data commands, it downloads the latest data for a prediction, it then processes that data, which is you referencing the training data for normalization parameters, and then processing that data. It creates a configuration-only data set, so we don't need to cache the data. It uses the run predict ensemble to actually make the predictions across all of the different models that were trained, and then we upload, as I say. As I said, we're using cron, which is the Linux inbuilt scheduler, but you could use other workflow managers quite easily because of these command line interfaces that we've provided. I've mentioned before as well about extensions. So that one of the reasons why we lower the barrier to entry with command line interfaces, but by providing a Python package that's well organized in terms of class hierarchy and functions or functional components, we make it really easy for researchers to actually develop their own extensions to it as well. There's 3 areas you might want to do this in. So there's the data sourcing, which are the IceNet data commands, the data pre-processing, which are the IceNet process commands, and then training and predicting. So the IceNet data and the IceNet process commands are actually built around a class hierarchy, and it roughly follows this structure, or it does follow exactly the structure at the top level. So you can inherit new downloaders, or you can implement new downloaders based on these root classes that have common functionality. So you see we've got methods like regrid and rotate win data that you can inherit, and that's actually to make sure that climatic data fits the sea ice concentration data uses ground truth, so that it can all be used as part of the input to the network. So it just lowers that barrier to entry to extending as well as using the existing functionality. In the case of training and predicting, is slightly different. It's actually a more functional. It's a functional approach to implementation, whereby you can actually just create your own function which implements a model as you see fit. And as long as your data is obviously prepared appropriately using the above implementations, then you can swap out the UNet, for example, with potentially new model implementations, which is obviously going to be good as we experiment further. So moving on to integrations and applications. Ooh, I've lost my mouse again. Moving on to integrations and applications. So as we saw earlier, we have this sort of 4-layered, 4-tiered framework that forms the core IceNet framework. So this is just so that we can provide data in a variety of formats for a variety of users. We provide CF compliant NetCDF so that it's easy for people to use, researchers to use the data directly. It also makes it very easy to integrate with platforms like Pangeo, which we're hoping to do in the future. And obviously you could also look directly at the data store if need be. There are other upload commands. So for example, copying to central data stores in BAS is something that we do at the moment on a regular, just so that people can experiment with the data in terms of new integrations like the SDA digital twin and the Antarctic digital twin. We have an API, so the IceNet's PyGeo API instance, which James created, allows people to download the forecast as GeoJSON, which is really, really useful. And there's notebooks that demonstrate how to do this. I'm very conscious of time, so I don't want to spend too long demoing stuff, but I have actually set up the PyGeo API. So that is an OGC compliant API instance for which people can then easily integrate, which is great for application and web developers. And then we have visual applications. So I've got a little locally hosted toy interface, as I call it at the moment, because it's not really it's not used for anything in particular at the moment. But this just gives us an example of how we can ingest the various forecasts that have been output. So this comes via the PyGeo API and then is integrated with a tool called Cesium, which is quite CPU hungry, but it does give you a fancy globe, which is always cool to see the forecasts on. So you can imagine that you could actually, with a bit of with not a lot of effort, you could actually then tie that API to a very workable interface for future development. So coming out from the framework even further, we then have to think about, well, when people start to ingest that data, you're then looking at the ecosystems that IceNet's involved with. And this is where I'm really happy to say we're beginning to get some real interest in some and have some great fun. So one of the things we're doing at the moment is developing within BAS. We have a team of developers who are working on a route planner to optimize the routes taken by the ship in conjunction with the SDA master who drives the boat. So IceNet forms part of this picture in that the forecasts are fed into the route planner, which also takes in a host of other datas. And it then outputs plans into something called a Sea Ice Information Service, which is hosted on the bridge of the ship. So this is an ongoing development, as I say, it's not in production yet, but and then this is part of our digital twin, because actually as the ship's master makes alterations based on the decision-making aids that are provided, obviously we then pull data in, which all then gets fed back into the same system in order to produce further advice about which routes might be best to take. And this is one element of a much larger digital twin that will develop over time, also involving IceNet. IceNet is involved with, you might see down there, an Antarctic digital twin as well. I won't go into that just yet because I don't have any graphics for it. Here you'll see this is a very early days, but the original route planner software, which was developed by Professor Maria Fox, I actually integrated the IceNet forecasts into it at a very early stage for 2020, and we see here that actually it did do some planning with the data on a grid. These are quite trivial examples, but the team have been working much more comprehensively, and I've included one of their videos. I hope they don't mind. I did ask permission actually, which shows the routes. So the blue is the SDA itself, and the red is the route planner's advised routes. Obviously, the blue deviates somewhat. Now, this is just because of the nature of the data they're taking in, but you can see how this development process is ongoing and will ever increase in accuracy and functionality, providing a really, really valuable decision-making aid for the future. So what is the future of IceNet? So we're currently validating the daily forecast. That's a topic of great research, great and active research. We have digital twin developments, as I say, with the Antarctic and the SDA digital twin. These are really important for driving IceNet forward as well, because they help with the way that BAS operates, and no doubt will be of great interest to the Turing as well, because it's a really cutting edge AI system. We are looking at external partner collaboration. So if anyone's interested, then always welcome to get in touch and propose something to us. We've got a few in the pipeline which are very exciting, which I won't go into now. We're going to establish a production framework. Currently, this is all internal. Like we're currently working on, as I say, validating the forecast, but also the how we scale the platform horizontally. It's designed with that in mind, but it's not currently open for public consumption just yet. And then we're going to look at how we're publishing the product. So the research, the data, and the code will all be published in due course. So some conclusions, just to finish up. The research is ongoing. It's something that we're actively looking at. So we're always interested to hear from people on that count. The ecosystem is maturing. The more integrations we do and the more adoption we have, the better it gets. So if you're an adopter or collaborator, then we're always interested to hear from you. But that is a little bit slower than I originally did it, but it is a very quick run through. And now it's time for some Q&A.
So we have Bernard, who's been patiently waiting this whole time. Bernard, I'll let you in, and hopefully you didn't lose track of your question. Oh, we lost him.
We lost him. Oh, no.
So if anyone would like to ask a question, you can use the button in the top right to ask to unmute, or you can put it in the chat. So we have this collaborative document. I don't know if you guys saw, because I just put it in the. Oh, Scott has a question. What is a digital twin?
Yeah, so that's a really good question. So a digital twin, for all intents and purposes and in simple terms, which are the best terms, is a virtual representation of a real world system. So the reason why we call it a digital twin and not a model or a simulation or an emulation is because it's an active feedback system, feed forward system. So we're looking at a digital twin in some way influences the real world and then takes in data from the real world in order to produce the decision-making aids that will then be part of the cyclical nature of influencing the real world. Hopefully that answers the question quite accurately. It's a very contentious term actually at the moment because many people have very many different understandings, and of course the concept of doing this is not entirely new. But yeah.
So Sophia is asking, are you planning to work with the Met Office Informatics Lab?
I can just say that I have some collaborators at the Met Office Informatics Lab, although it's actually on an altogether different project, so nothing to do with sea ice forecasting. But the BAS AI Lab, we're friends with the Met Office Informatics Lab, and I'm sure we'd be happy to kind of explore what potential synergies and things there might be with obviously their vast experience of running forecasts in real time, of course.
And on top of that, actually, I have talked about with them about data access as well, and the sort of data that we could actually feed into the pipeline. So that's still an active. The data forms that we've used were influenced directly by Tom's paper, and there's no reason why we can't look at others in the future if they're relevant. So we have been chatting with them a little bit.
So we have Andrea asking, do you know when the data and codes will be available outside the project? Which is something we spent a lot of time talking about.
Yeah, it's a really good question, that, and we're very much believers in open source to varying degrees, but it is still open. It is still a research affair in terms of developing the model. So there are portions of the code that are available. So in the document, I've linked the IceNet project repository. And if you go there, then you can see not only this notebook, but you can see the demonstrator notebooks. You have all of the ETL pipeline and API provisioning codes are available. The model code from Tom's original paper is available in his repository. I think that's linked in the document as well. But the active model code that we've talked about herein, we're waiting for a preprint on the paper to come out before we release that.
Thanks. So Sophia asks, have you explored whether CMIP model biases will produce incorrect IceNet predictions?
Yeah, I can attend to that question. So CMIP, that's a term for climate simulations for anyone who doesn't know. And in the kind of proof of concept IceNet research, we pre-trained the model on climate simulations, so it learns how to forecast the ice in an entirely simulated world, of which there's a much greater abundance of data, before we kind of start showing it real world observations. So my comment towards that is that yes, there are errors in the simulations due to approximations of physics and limited spatial resolution of the simulations of the Earth system, and that would affect how well IceNet produces its forecasts. That's correct, and it would involve biases. What I kind of did to mitigate that is that I trained simultaneously on multiple different climate simulators, so it wouldn't focus too much on the biases of one particular simulation, and also that's the first stage, and then it moves on entirely to learning from observational data, which gives it the chance to correct or kind of unlearn any biases that it picked up from the pre-training phase using the simulation data.
Great, thanks. And just a reminder, if anyone wants to ask their question on video or even audio only, you can do that in the top right corner. There's a button to ask to unmute. But I'll go to the next one in the chat. Aled, I'm sorry if I'm pronouncing your name incorrectly. He says, really interesting talk. Are you encoding any details of the model run in the forecast net CDF?
So we do enter some attributes in the global attributes for the file that tell you where the file's being produced from. So that's part of the AUCCD convention, or the variables that basically say what model produced it, produced the forecast, and what version of the code produced it as well.
Okay, and we have one last question from Marcus. He says, could you give a quick estimate of how much work it was to go from a researchy proof of concept to your infrastructure that you can now easily share with others? That's a good question. I feel like it's a lot.
That's a really interesting one, isn't it? So, I mean, in terms of the length of time it's taken, I mean, Tom, I think you published in August last year, was it, your Nature paper?
Yeah.
We were working on this beforehand, so I helped Tom a little bit with some of the coding elements of his original research. And then we put a project together. So I think the timeline, James Robinson, was 8 months on the project, was it not?
Yeah, so I mean, it was like 3 months equivalent of my time, because I was only working like 40% of my time on this project. I don't know how much of your time it was.
Yeah, so it's probably about 40% of my time as well.
Yeah, so probably about the same. So probably about 6 months in total between us.
Yeah, exactly. And then, but we've had some interesting asides to that as well. A bit of a shout out to the Judge Business School. Tom and I actually collaborated with them on a Cambridge Venture project that sort of explored how we might progress IceNet as a sort of social initiative. So, you know, we were collaborating with them and doing lots of little extra bits on the side, as well as just doing the tech implementation. So I would say, yeah, one person is about a 5-month, 6-month development effort in order to produce the surrounds. But bear in mind, a lot of this has been ported, a lot of the model code was ported from Tom's original research code, which is currently available. So.
I think it's a fascinating question and kind of gets to the root of what we've done in a very general sense. So if you kind of abstract away from what I, in my biased opinion, are the very interesting technical details and the deep dive of both your work, both the James's work, and also the CI specific stuff. Once you abstract away from that, what's happened is there's been a kind of proof of concept computational research study done, which has resulted in a research code base. And there are requirements of that kind of work, like, you know, you have time constraints, all these other things. You just want to get results as to a certain extent as quickly as possible to see if is there actually an idea here, is there something publishable, is there potential here. And then there was obviously the second phase with the operationalization, deployment, refactoring that whole initial code base. And I think there are a few kind of interesting learning points from that, at least for me. And I think one of the interesting things is I wouldn't have dramatically changed like the way I wrote the initial code base. There would be details, small detail changes, like perhaps focusing on a more object-oriented approach and a more modular approach, and some things that I've picked up, small technical details from the work of this extension of the code base. But at the end of the day, as a researcher, you kind of do just have to get the results as best as possible. But I've really learned that it's not a major headache or a massive burden of time to actually just make these small changes that actually lend themselves so much better to potential deployment and operationalization of your research. And I know that's actually quite rare in research these days to have, say, a machine learning system deployed from academia or something and start running in real time. So I'm very lucky in that regard. But it is worth just thinking about potential future extensions as you go along. But you obviously, I do acknowledge that there is a real need to focus on getting results in the best way that you can.
And I would say this is, this is where the value of the Turing collaboration is. It's also why organisations like the Software Sustainability Institute exist as well, and even the very concept of research software engineers is that, industry has had decades to work out how to build sustainable operational software, but sustainable research software is a very different matter, and it's something I'm learning a lot about as well. So yeah, it's been a very interesting journey for us, I think.
That's exactly what I was going to say. This is a great example of how the Turing and BAS have collaborated, and the kind of work that we can bring different skill sets to help move it forward. So that's great. Yeah. Anybody else? Any more questions? So if you go to the Google document that is pinned at the top of the chat, you'll see contact info about following up. So you've got James and Tom's info, and then also there's a RAM email address and a partnerships email address. So if you have any follow-up questions, feel free to email us there. But yeah, is there anything else you three wanted to bring up, or do you have questions for the audience?
No, but I would reiterate those. Please do follow up. Like, we're always interested to hear about how people think this ecosystem and framework, and even the modelling itself, might be applicable. This is quite a new venture, so it's good to reach out.
So we did just get one more question about: are you working with the scientific committee on Antarctic research?
Interesting. Tom, you probably best placed to answer that.
I'm not working directly with them, and I must guiltily admit I actually haven't heard of this institution before. So I'm going to go and look this group up straight after this workshop.
So we do have a lot of researchers at BAS who are members of SCAR. Or
James's connection dropped.
Oh, sorry. Have I reappeared now?
Yeah, you kind of glitched out for a minute there.
Okay, so I was just saying that BAS do have lots of researchers who do actively work with SCAR, but as a development group, we haven't. But the PI on the project, actually, Scott Hosking, would definitely be able to answer that question.
Great. Well, I don't know if Scott may have dropped off. I'm sure he's got a lot going on today. So yeah, this was really great, everybody. Thanks for joining, and thanks for your questions. Thanks to James and Tom for your time and your presentation. And yeah, just a final reminder, just grab that link to the Google Doc, and that's where you're going to find the link to James's notebook that he presented. So you can have that info, and you know how to get in touch. Awesome. Thanks, everybody.